We will now turn our attention to gravitational potential and gravitational potential energy. As I've explained in the previous slides, near the surface of the Earth, the gravitational field lines are evenly spaced and parallel. Hence, we can assume that there's uniform gravitational field near the surface of the Earth, and g can be taken to be constant, around 9.81 meters per second, near the surface of the Earth. So when we want to find the change in gravitational potential energy from the surface of the Earth to a height h, we can use the expression mgh. However, if we move to a distance that is much further away from the surface of the Earth, then we have to be careful as g is no longer constant. It will decrease as 1 over r squared. To have a more complete understanding of this, we will have to have a proper definition for gravitational potential energy. Gravitational potential energy U is defined as the work done by an external agent in bringing a body from infinity to that point, without any change in the Ke. To understand this statement, let us consider a mass m, this yellow mass, that is at a distance that is a very big distance, far away from the center of the Earth. And we will represent this distance by r equals to infinity because it's really far away from the center of the Earth. And we will set this point as the reference point where the potential energy is 0. Now what happens if you allow the yellow mass to move towards point P? Under the influence of the gravitational force Fg, the yellow mass will accelerate and move faster and faster. In order for it to move without any change in Ke, we will need to have another force that's exerted by an external agent to balance Fg, such that it can move without any change in Ke. So what do you notice here is that the direction of Fe is opposite to the direction of the displacement of the mass. In other words, we will have the negative work done by the external agent. Okay, and this explains why in the expression of U, you have a negative sign. The next thing we can check that this expression makes sense is that when r equals to infinity, that is our reference point, U is 0, right? The gravitational potential is defined as the work done per unit mass by an external agent in bringing a body from infinity to the point. It is closely related to gravitational potential energy. You just have to take U divided by m to get phi. Notice that both gravitational potential energy and gravitational potential are scalars. Let's now see what happens when we sketch U or phi against r. This is the form of the graph that you will get. A graph that is always under the x-axis. And this value is always negative. The maximum value of U or phi is actually when r is very big. And it will decrease as you get closer and closer to the Earth. This is consistent with what we have experienced so far, even when we use MGH, right? The higher the object is, the higher the potential energy. And when the object reaches the surface of the Earth, the potential energy decreases. Now, the one key difference between this formulation and the one that we are so used to, the MGH formulation, is that we have chosen the reference point in this case as r equals to infinity, u equals to 0, whereas we are very used to setting u equals to 0 on the surface of the Earth when we are working near the surface of the Earth. Next, it's quite useful to be able to derive the formula for gravitational field, the force from U and vice versa. You can differentiate one to get the other and integrate the other to get back the U. So to summarize, note that the formulas for gravitational potential energy and the gravitational potential, note that they both come with the negative sign, and do not use U equals mgh for questions that have the big values for the distances from the surface of planets and Earth. In terms of the graph, you should be able to determine the direction of the force if you are given the UR graph. Alright, so just look at this. If let's say you are looking at this point, okay, and I ask you what is the direction of the force if the mass is placed at a certain distance from the surface of the Earth. Okay, so this is where the surface of the Earth is. If you have a mass here, you know that the force is given by minus du dr. So du dr is positive, right? As can be seen from this blue line, it's a positive gradient, but the direction of the force is in the negative. It's negative ur, so it's actually in the direction of the negative r, right? So that's the direction of the force. Okay. You can also do the same kind of analysis for the phi r graph. Let's summarize the relationship between the four quantities in this table. So how is G and F related? G is just F over M. Okay, we go diagonally down. Phi is U over M. Okay. Then F is negative of the derivative of U and R. And G is minus d phi dr. Okay. And these are the two key points that you need to take note when we work with gravitational potential and gravitational potential energy.